君の虜になってしまえばきっとこの夏は充実するのもっともう戻れなくたって忘れないで
My name is Syarah Nurfarhana Binti Shaharudin, matrix number 1170877. Today, we will present about industrial fermentation. In this chapter, I will explain about the introduction and history of fermentation, food and feed treatment by fermentation, and social and economic aspects in industrial fermentation. Okay, the first one is introduction and history of fermentation. Okay, so first of all, we have to know what is fermentation. Fermentation can be defined as the alteration or production of products with the help of microorganisms. Fermentation has been used to conserve and alter food since long time ago. Fermentation was a method of choice to convert fresh agricultural products into durable food items. A few examples of fermented food products that we all know, such as soy sauce, vinegar, yogurt, and many more. Fermentation can be spontaneous or be induced by specifically added microorganisms. And everyday examples of induced fermentation is the addition of baking yeast to flour to make breads and cakes. Next, the history of fermentation. Since around 1800s, the mechanism of fermentation has been studied in a scientific way. It started in 1818 when a German scientist, X. discovered that yeast induces fermentation. So this is when the yeast was discovered as the origin of fermentation. In 1857, Louis Pasteur, a French scientist who made a lot of contribution in microbiology, discovered the scientific explanation for lactic acid production. Louis Pasteur explained that bacteria produce lactic acid, which then conserves the food. He also noticed that unwanted fermentation can be stopped by heat treatment of the substrate, which is pasteurization process. This technique is still widely applied to treat milk and fruit juices. In 1881, production of lactic acid became the first non-food industrial application of fermentation. Since around 1900s, an important milestone was the introduction of biological wastewater treatment by fermentation. Modern industrialization started around 1900s, so many people migrated from agricultural area to the big cities, which causes public hygiene become a major task. Therefore, it was a big step forward when biological wastewater treatment plants and public sewage system were introduced. In 1910, industrial production by aseptic fermentation was discovered. The first aseptic fermentation on an industrial scale was the production of acetone, butanol, and butanediol for rubber production. In 1928 and 1929, this is when the penicillin was discovered. Penicillin was the first antibiotic and the first really effective medication against a bacterial infection. Since 1960, amino acid production by fermentation started in Japan. Since 1980, this is when genetic engineering was developed. The introduction of genetically modified microorganisms and production of insulin also occurred during this era. Insulin was the first commercial product using genetically engineered bacteria for fermentation. Today, many different fermentation processes are applied in industry. They range from large-scale low-tech processes to a very sophisticated biotechnology processes.
Hello guys, okay, let's move to the biochemical and processing aspect of fermentation process. So in this subtopic, we will discuss in detail about the principle of the fermentation process. For your information, nearly all fermentation process follow the same principle, which is there are 4 main stages, which are the first one is the starter culture, the second one is the fermentation substrate, the third one is the fermenter, and the fourth one is the downstreaming process. So the fermentation process started at the starter culture. So the seed of the microorganism desired is added into the starter culture. Then the second stages, which is the fermentation substrate. Substrate is also called as the feed of the microorganism added at the first stages. The substrate will react with the seed of the microorganism that has been added in the starter culture in the fermenter. So both of these elements will be reacted in the fermenter. So by the end of the reaction, a complex broth of fermented products is being produced that contain bacteria, water, undesired bacteria, and so on. So the broth needed to be purified and separated in the downstreaming process. So let's move to the microorganism. In this subtopic, we need to know what type of microorganism used in the fermentation process and what are their criteria. There are 2 types of microorganism used in the fermentation process. The first one is the single cell microorganism. The second one, the cell aggregates. So what is aggregates? Aggregates mean the cell is loosely grouped together, which the cell are not packed to each other. So the bacteria in the microorganism contains several elements, in which the first one is the cell liquid, cell wall, DNA, plasmid, and plasma membrane. So in the cell liquid consists of vitamins, enzymes, and proteins. In the cell liquid, it contains things the cell needed to populate. Populate means to multiply. So the second one is the cell wall. The cell wall acts as the protection of the cell. And the third one is the DNA. The DNA carry the genetic information of the bacteria. The next one is the plasmid. The plasmid is the independent DNA unit. It is important in transfer genetic information of the bacteria. The last one is the plasma membrane. It allows transport of nutrients in and metabolites out of the bacteria. So next we move to the culture development of the fermentation process. So in order for us to get the best product out of the fermentation process, first of all we need to get the best culture in the first place. So the selection for the best culture needed to be developed in terms of the selectivity and the growth characteristic includes the pH and the temperature sensitivity. So in the culture development, the technique used is mass screening techniques. There are 3 main stages in the mass screening techniques. The first one is the primary screening. The second one is the secondary screening, and the final one is the genetic improvement technique. So for the primary screening, it will yield, for example, 10 strain of microorganism. Then the 10 strain of microorganism will be filtered by the secondary screening. Maybe only 4 strain of microorganism is useful and the other 6 is a defect. But for your information, although the primary screening and the secondary screening yield strain of microorganism, the quality is not good enough to be used for the large scale. The genetic improvement technique is added for us to get the best strain of microorganism that can be used in the large production scale. So next we move to the starter culture storage. So after we get the best culture at the mass screening techniques, so we need to store the culture in the optimized condition so that the microorganism retain in terms of stability and variability. So there are several methods that can be used. The first one is to keep the microorganism in agar plate. So what is agar? Agar is a substrate that contains all nutrients that the microorganism needed. The cell can stay alive in the agar plate for a while until all nutrients in the agar plate are used up by the microorganism. Then, after all the nutrients have been used up, then the microorganism will be transferred into the new plate. So the next method is lyophilization. So what is lyophilization? Lyophilization is when the cell is shock frozen and the water from inside of the cell is removed by evaporation in the condition of low temperature and low pressure. The cells that undergo this process are stored in long time with minimal maintenance, and only robust cells are survived. The next method is the cryopreservation of cell. So in this method, the cell suspension in aqueous glycerol or the MCO are shock frozen. The cell is stored in liquid nitrogen or dry ice. As the cold chain needed for the cryopreservation of cell, a continuous supply of nitrogen is needed for this process, or otherwise the process will be interrupted and the microorganism will be disturbed. So next we move to the process development. So there are three stages of fermentation process development. The first one is the screening process, the second one is the lab scale fermenter, and the third one is the pilot plant fermenter. So the purpose of the first stages, which is the screening process, is to obtain the best possible reaction condition, the best possible optimal media, and the last one is the best possible microorganism. So for the screening process, the scale is much more smaller, which is performed in milliliter scale. For the next stage, which is the lab scale fermenter, in this stage, it measure the parameter changes, in which the pH change, the oxygen change, the growth of the microorganism change, in which the lab scale is to optimize the fermentation process. The lab scale fermenter occur in liter scale. Last but not least, the pilot plant fermenter. The pilot plant fermenter occur in several hundreds liter of volume of compared to the lab scale fermenter and the screening process. So the pilot plant fermenter is set up as close as the large scale fermenter. This is because the pilot plant fermenter acts as the indicator for the fermentation process to be used at the industrial scale. So we move to the factor of fermentation process. So there are 4 factors, in which the first one is mixing, the second one is heat transfer, the third one is stability of biological system, and the fourth one is the cost of fermentation medium. So for the mixing factor, we need to note that different scale have different condition of mixing. For example, it takes only several seconds in lab scale for the mixing process to finish, but it would take hours for the mixing process to finish for the pilot plant scale. Second one, the thing that we need to consider in the mixing process is that microorganism is sensitive to mechanical stress, so vigorous agitation or stirring is not possible during the fermentation process. So the second factor is the heat transfer. In the heat transfer factor, the cooling system needed in the large scale reactor is to keep the temperature in an optimal range. This is because the small changes in temperature may lead to consequences. The first one, small changes in temperature may lead to fermentation process to be stopped, and the second one, it may lead to different types of microorganism, which may lead to wrong direction of reaction. The direction of the reaction may be backward. So the third one is the stability of biological system of the microorganism. The term stability here brings the meaning of how many generation of microorganism can be used for production before the microorganism degenerate. So the bacteria have several generations per day because the bacteria regenerates in the scale of hours. So if you want to commercialize the microorganism, there are several characteristics that we need to consider. The first one is mutant or genetically modified cells. The second one is the microorganism need to be less robust. The fourth and the last factors of fermentation is the cost of fermentation medium. So the constituent of medium must contain the composition of biomass, in which it must contain carbon, hydrogen, nitrogen, oxygen, and sulfur. So next we move to the bioreactors. The bioreactors must fulfill a number of requirements to be suited for large-scale production, such as efficient mixing. Bioreactors must allow efficient mixing in order for the microorganism not to be in a mechanical stress. Like I said before, if the microorganism is in mechanical stress, it may cause damage in the microorganism itself. And the second one is it must allow temperature and pH control, and the third one is the efficient oxygen production in the bioreactors. The next one is the online measurement of the process parameters, and the last one is it need to be easy to clean and sterilize, which means after the fermentation process have been occurred, the bioreactors needed to be clean. So easy to clean bioreactors may be the best suited for the large scale production. Bioreactors come in many different design and shapes. So as you can see, there are two common fermentation reactor, which is the stirred tank reactor, and this is the airlift reactor. What is the difference between the two reactors? So the stirred tank reactor have the mechanical stirrer. This one is the mechanical stirrer, which will mix the fermentation broth, but the airlift reactor use oxygen or air to mix the fermentation broth inside the fermenter reactor. So the last part is the downstream processing. As I mentioned earlier, after the seed of the microorganism and the feed of the microorganism is reacted in the fermenter, it will produce a fermentation broth. So the fermentation broth or the chemicals produced by the fermentation contains many components such as the water, undesired strain, bacteria. So the downstreaming process is needed to separate the products from the other products of the fermentation broth, and it is tedious and often the main cost factor. So for information, the 60 to 95% of the total cost of the fermentation to produce a product is for the product recovery, which means the downstream processing is, as I can say, the main stages in the fermentation processing. Okay. Step in downstream processing. There are several steps. The first one is the separation of cell. The second one is the filtration, and the third and the final stages is the final purification and conditioning of products. So in the separation of cell, the best and the easiest way to separate the cell from the liquid is by sedimentation. The sedimentation process occurs if the cells are heavier than the liquid, then they will accumulate at the bottom of the tank when the agitation process is stopped. Then the next one is filtration. Under filtration, there are several ways in order for us to filtrate the cell from the liquids. The first one is by using the membrane filter. The membrane filter is a classical deep bed filters which is semi-permeable polymer tubes or plates that separates liquids from the particles. The next type of filtration is by filtrate through filter medium. It is practical application, however, it can be difficult because of the widely differing particle size of the medium inside the liquid. So the next way of filtration is by using the ultrafiltration, and the fourth one is chromatography technique, and etc. So after fermentation process fermentation product undergo the separation of cell and the filtration process, then the final purification and condition of products occur. In these stages, the chemicals and proteins are often recrystallized and heat or freeze dried.
I am Asyiqeen Binti Muhamad Zaki.
On your own, and here it goes. I'm just a kid.
And I'll be continuing this presentation. We will go to the subtopic Industrial Chemicals by Fermentation. So before we go, under this subtopic, we'll be discussing on 4 industrial chemicals that is produced by fermentation. They are ethanol, amino acids, vitamins, and enzymes. So for the first one, ethanol. As we all know, ethanol is a primary alcohol with many industrial uses, and some of them are ethanol. Ethanol is used as an important solvent in the synthesis of other organic chemicals, and it is also the starting material for cosmetics and pharmaceuticals.
and in medicine it is used as disinfectant. And the largest potential use of ethanol is as car fuel in the automotive industry. So in the production of ethanol, ethanol is produced from sugar-containing feedstock, and this is the overall biochemical reaction in producing ethanol. Sugar is fermented and producing ethanols and carbon dioxide and energy. So, examples of sugar-containing materials are including fruits, sugar beets, sugarcane, wheat sorghum, and so on. Steps of producing ethanol. There will be 5 important steps producing pure ethanol, which are feedstock preparation, fermentation, separation, distillation, and dehydration. So, for the first feedstock preparation, the starting material is crushed to extract simple sugars, and starch. The starch will be converted to sugars in 2 stages: liquefaction and saccharification, where water and enzymes is added and also heat is used. This is also called enzymatic hydrolysis process. Second step, fermentation. In the fermentation, the mash is transferred to fermentation tank and cooled to optimum temperature around 30 degrees Celsius. Then yeast is added, producing alcohol with concentration of 8 to 12%. Third step, separation. Stripper distillation is used to separate liquids from the solid. The residue contains microbial biomass and water. They are called stillage. Stillage is then removed to prevent clogging in this step. The fourth step, distillation, which is fraction distillation, is used to separate ethanol from the water, producing 96% ethanol. As we know, this is the highest concentration that we can get from the fractional distillation because of azeotrope formation. So, if you want to get 100% pure ethanol, we need to further dehydrate it to reduce the rest of the water. So that's why we have to go through the fifth step, dehydration. Dehydration can be used by molecular sieves or carrier-assisted distillation to produce anhydrous ethanol, which is 100% concentration ethanol. Next, amino acids. Amino acids, or other names, L-glutamic acids, and its salts, monosodium glutamate, MSG. We know that it is an additive to human food to enhance the taste. This MSG has a very long history. To cut it short, in ancient times, people used seaweeds to enhance the food, the taste of the food, and only on 1908 that they know the essential component responsible for the flavor from the seaweed is glutamic acid. So from 1910 until 1956, the MSG was extracted from the seaweed. It was a very slow and costly method. However, in 1956, Ajinomoto, a Japanese company, succeeded produces MSG by fermentation. Until today, MSG is produced by microbial fermentation using genetically modified bacteria, where the fermentation uses glucose-containing organic feedstock and the L-glutamic acid is excreted by the cell into the surrounding liquid medium. Today, MSG is manufactured on a very large scale in many countries as it is used an additive to many food items, and the worldwide production is estimated to be 800,000 tons per year. And until today, with the progress of biotechnology, the cost of production of each amino acid has been significantly reduced. As you can see here, there are many starting material that can be used to produce amino acid. Next one, vitamins. Vitamins are produced by fermentation of sugar-containing starting materials and special additives by bacteria or yeast. For vitamins, the process parameters are similar for all vitamins. The difference is only the additives, which is the essential components of the vitamins. So as you can see here, these are the 5 main vitamins produced. The first one is vitamins A1, also called retinol. It is produced from beta-carotene, which can be obtained by fermentation of corn, soybean meal, kerosene, thiamine, and alpha-ionine. For vitamins B2, riboflavin. This vitamin is produced by yeast from glucose, urea, and mineral salts in an aerobic fermentation. Aerobic fermentation meaning that the fermentation is undergo with the presence of oxygen. If it is anaerobic fermentation, the oxygen is discharged and is replaced with either nitrogen, carbon dioxide, or any byproduct of the fermentation process itself. Okay, next, vitamin B12, cyanocobalamin. It is produced by bacteria from glucose, corn, and cobalt salts in anaerobic and aerobic fermentation. For vitamin C is produced by Acetobacter suboxidans bacteria from sugar compound desorbate to L-serbose. L-serbose is then converted to L-ascorbic acid, that is better known as vitamin C. Next, vitamins D2. It is formed by photochemical cleavage of ergosterine, which is a side product of many fermentation processes. Microorganisms usually contain up to 3% of ergosterine. Okay, so vitamins, they are also isolated in crystalline form and is used to enrich food for human use. Okay, lastly, enzymes. So enzymes, we know that they are the active components in the cells where they induce chemical transformation. So in fermentation, enzymes are often obtained from the waste bacterial biomass that remains after food fermentation process. So these are some important examples of enzymes. First one, protease. Protease are added to detergents to enhance the hydrolysis of protein-containing stains, and about 80% of all detergents contains protease. Next, acidic protease. They are isolated from yeast and are used in food industry to help produce cheese, soy sauce, and baking products. Amylases. Amylase cleaves starch into amylase and amylopectin. It is applied in paper manufacturing and food industry. Next, glucomylase. Glucoamylases help to hydrolyze oligosaccharides to glucose in fruit juice, enhancing the taste and removes turbidity. Other than that, enzymes are also used in clinical and biological analysis. And the best known example in this case is peroxidase. Peroxidase is used as in the indicator strips to diagnose diabetes by measuring sugar levels in urine and blood. That's all from me for this subtopic. Thank you.
Hi, Assalamualaikum. My name is Rahainahnajiha binti Rahman. And I will explain about pharmaceutical products by fermentation. Pharmaceutical products by direct fermentation. Although most research is devoted to the biological and pharmacological problems, the key step in the actual production of biotech pharmaceutical is fermentation. Penicillin was the first highly efficient antibiotic pharmaceuticals that allow an effective treatment of bacterial infection by fermentation. Penicillin was discovered in 1928 by Alexander Fleming. He observed that the growth of bacteria culture was inhibited by a fungus, Penicillium notatum. The naturally growing wild type of Penicillium notatum produced penicillin with a yield of 10 mg per liter. The old method of growing the penicillium mold on the surface in the medium in liter-sized flasks, and then it changed to fermentation in large aerated tanks. The mold can grow throughout the entire tanks and not just on the surface of the medium. Today, penicillin and other antibiotics are produced in large-scale fermenters holding several hundred cubic meters of medium, and the yield has increased 5,000-fold to 50 gram per liter. This is the simplified scheme of the biosynthesis of penicillin. It starts with the amino acid, La amino adipic acid, and L-cysteine from penicillin and
in a complex reaction sequence. When phenylacetic acid is added to the fermentation medium, the side chain of the molecule is modified and the resulting product is called penicillin G. Pharmaceuticals via biotransformation. What is biotransformation? Biotransformation are chemical reactions that are induced by enzymes in the cells. Sometimes it is possible to isolate the enzyme and to carry out the chemical reaction in a separate reactor in the absence of living cells. The starting materials are single chemical compound or mixture of related compounds which are converted to the product with high selectivity. Specificity has several levels. First, conversion of one compound in a mixture of similar compounds or conversion of only one functional group on a complex molecule with many functional groups. Many biotransformations are difficult to achieve by conventional synthesis. For example, the synthesis of chiral molecules we call enantiomers. Chiral molecules, the definition is it can occur in two forms that are mirror image of each other. The classical synthesis produces both enantiomers in a 1:1 ratio. They cannot be separated by normal physical means. Nature is, however, more selective. Here, only single enantiomers are formed. This can be utilized to separate DL enantiomers of amino acid. The enzyme L-amylase produces selectively the L-amino acid from a mixture of the D-L-acyl amino acids. The next part is the advantages and disadvantages of biotransformation. First, the advantage of biotransformation, they are very specific. They also allow conversion of otherwise unreactive groups in a molecule. It also can be carried out under mild condition in an aqueous solution. And then the disadvantage of biotransformation. It is difficult and expensive to isolate the products from the reaction mixture. The last part is biopolymers. What is biopolymers? Biopolymers refers to polymers that are used as materials in industry. For example, xanthan gum and scleroglucan. Xanthan gum is water-soluble heteropolysaccharide with a very high molecular weight, more than 1 million, produced by the bacteria named Xanthomonas campestris. The function is act as a stabilizer for sauces and dressings. The next is scleroglucan. Scleroglucan is water-soluble non-ionic natural polymer produced by the fungi named Sclerotium rothschild. The function is for thickening drilling muds and enhancing recovery. Biopolymers are also used in adhesive, watercolor, printing inks, cosmetic, and in the pharmaceutical industry. For example, polyaptites and dextran. Polyaptites made from lactic acid and are used for orthopedic repair materials. It also can be absorbed by the body and are used for the treatment of porous bone fractures and joint reconstruction. The next is dextran. Dextran is produced by fermentation of saccharose by microorganism named Leuconostoc mesotroides. It is substitute for blood plasma in medicine. That's all from me. Thank you.
For the next subtopic, which is food and feed treatment by fermentation, I will explain about food conservation, feed and agriculture, and single-cell protein. First one is food conservation. As I mentioned earlier in the introduction, fermentation has been used to conserve and alter food since ancient time. Until today, it is still applied on a very large scale for this purpose. There's a few examples of food conservation such as sauerkraut, soy sauce, and milk products. But in this chapter, I will only explain about the conservation of sauerkraut, since the principle is similar in most cases. So basically, the principle of fermentation is lactic acid, which is produced by bacteria, protect the food by inhibiting the growth of mold and other microorganisms. So most of the vitamins and nutrients of the food are preserved during fermentation. Sauerkraut. What is sauerkraut? Sauerkraut is fermented white cabbage that is used by early settlers to fight scurvy, a disease that is caused by deficiency of vitamin C. So this is the picture of sauerkraut. So how sauerkraut is made? First, the cabbage heads are cut into 1 to 3 mm wide strips and placed in large concrete tanks in intermittent layers with salt. Next, the liquor of the previous batch is added as starter culture. Lastly, the tank is sealed and remain undisturbed for 4 to 6 weeks. So next, how the reaction sequence during the fermentation process. First, at the beginning of fermentation, aerobic bacteria start to grow. After all oxygen has been consumed, aerobic bacteria will die. Next, the process will become anaerobic. The lactobacillus cells from the starter culture grow rapidly and produce lactic acid. Therefore, the mixture will become more and more acidic. The acid will then inhibit the further growth of the lactobacillus cell and other microorganisms. Then after a few weeks, the whole process comes to an end and the product is removed and packed in plastic bags. This is the graph that shows the development of the number of cells during different phases of cabbage fermentation. So this is when the fermentation begins. At the beginning of the fermentation, aerobic bacteria start to grow. Then after all oxygen has been consumed, aerobic bacteria will die. This is the phase when the starter culture is added and lactobacillus cells grow rapidly and produce lactic acid. Then the lactic acid will inhibit the growth of the lactobacillus cells and other microorganisms. This is the phase when no starter culture is added, so the fermentation will start delayed. The reason for the delay is because natural lactobacillus cells contain relatively small number in fresh cabbage, so they need time to multiply to a level that leads to a significant lactic acid production. Next is feed and agriculture. Not only human food but green animal feed also need to be protected from rotting. This is to provide supplies during non-growing season. Silage is the largest volume product of feed and agriculture. Silage is a type of fodder made from green foliage crops which have been preserved by acidification achieved through fermentation. Silage also produced from fresh plants or plant parts such as green maize plants, sunflower foliage or sugar beets. So this is the picture of silage. So how silage is made? By compressing and shielding the green plants from air, which is oxygen, by strong plastic bags or concrete silos. This is the concrete silos. So the reaction sequence is similar as described for food, where aerobic bacteria start to grow until all oxygen is consumed. Then the anaerobic lactic acid producing bacteria takes over and produce lactic acid, which will protect the silage from rotting. The fermentation starts spontaneously, but it can be supported by adding minerals, sugar and inhibitors for aerobic microorganisms. The temperature must be in a range that tolerable for the lactobacillus microorganism. In moderate, cool climates, silage can be produced outdoor without special control. Next, single cell protein. Single cell protein or microbial protein is bacterial cells that have a high content of protein but are low in fat and cholesterol. That is why the name is single cell protein. Actually, single cell protein is the byproducts of all fermentation processes. Single cell protein mainly used as an additive in animal feed to enhance protein content. The starting materials for the production of a single cell protein can be anything from agricultural commodities such as sugarcane, maize or sorghum to petrochemicals such as paraffin, methane or methanol. For maximum cell growth of SCP production, it is desired to optimize the fermentation condition. This means sufficient carbon, nitrogen, water and other nutrients must be supplied, and an efficient addition of oxygen is important for aerobic processes because the oxygen transfer is often the rate limiting factor. The fermentation is usually continuous. It proceeds under sterile conditions at constant temperature and start with a defined starter culture. This is to avoid the side product as far as possible. Several processes had been developed. For example, Shell had originally introduced a process that used methane as the raw material for SCP production. The microorganisms are cultured in an aqueous medium at 42 to 45 degrees Celsius, pH value of 6.8 under semi-sterile conditions. The final fermentation broth contains protein at a concentration of 25 gram per liter. The biomass is concentrated in large sedimentation tanks and spray dried. The mass balance equation 9.3 shows that large volumes of oxygen are needed and that carbon dioxide and heat must be removed from the reactor. So this is the equation 9.3. Large volume of oxygens are needed. Carbon dioxide and water are needed to be removed from the reactor.
My name is Nabilah.
And we dance all night to the best song ever.
And I will be explaining to you about environmental biotechnology. When modern industrialization happened, many people moved from agricultural area to the big city. When this happened, public hygiene become a problem. This is because the waste are not treated and discharged properly, and this can cause a hygiene-related epidemic disease such as cholera and typhus. This problem solved when public water collection system is introduced at the end of the centuries. The degree of pollution of the wastewater is measured as BOD5 and COD. What is BOD5 and what is COD? BOD5 is biological oxygen demand, which is the amount of oxygen that is consumed during the microbial conversion of organic matter in 5 days. And COD is chemical oxygen demand, which is the amount of potassium permanganate solution needed to titrate a defined volume of wastewater. The modern biological wastewater treatment plants use a combination of aerobic and anaerobic fermentation reactors to remove organic matter from the wastewater. So again, what is aerobic and what is anaerobic? Aerobic is the microorganism feed on the organic matter in the wastewater and convert it to microbial biomass and carbon dioxide. Anaerobic is the microbial biomass of the aerobic part is digested by second type of microorganism that produce methane as it grows. Next, we will be moving on to the step in wastewater treatment. In primary physical treatment, solid material is separated from the liquid by screens, settling tanks, and skimming device. The remaining organic material is then subjected to the biological treatment, which is the step number 2. In smaller plants, the water is treated in open basin type reactor, which what we call aerated basin. In this reactor, oxygen is supplied by bubbling air through the water or by vigorously agitated the water. The bacteria inside the reactor will feed on the organic matter in the wastewater and consume the oxygen and then generate carbon dioxide. Then the bacteria, or now what we call sludge, will be sink into the bottom of the reactor and separated from the water, and this complete the aerobic treatment process. In large treatment plants of big cities, the open basin are replaced by more sophisticated reactors such as column reactor. Up to this point, 90 to 95% of biodegradable matter is removed from the wastewater. The remaining 5 to 10% is treated in clarifier basin, where the water is filtered and sometimes disinfected with sodium hypochlorite. The water then are safe to use or to discharge to the lake or river. Most of solid collected in primary and secondary treatment step are transferred to the digester, which is an aerobic fermentation reactor, which is often egg-shaped, as we can see right here. This is where the anaerobic microorganism convert the organic matter to methane, while the solid waste are then discharged while the methane is used to generate electricity and heat. As we can see, this is the diagram of wastewater treatment plant. This is the primary step, the screening step, and then this is the secondary step, the aeration tanks or open basic tanks. This is the egg fermenter, and this is the secondary treatment clarification for the water that free from the bacteria, and then this the water is disinfected and then discharged to the surrounding and can be drink or can be used. Fermentation is also used to treat industrial chemical or organic waste. The principle is very similar to the described anaerobic sludge treatment. Examples include waste containing cotton, rubber, plastic, fats, explosive, and detergent. Another example of the application of fermentation is the removal of organic compound from exhaust air using biofilter. Here is a diagram of the biofilter. As we can see here is the microorganism that grow on the solid support such as wood chips and porous stone. The microorganism here, for example bacteria, will digest the organic compound in the air and eliminate the odor causing chemicals. And that is the end of this subtopic.
Next, let's move on to the last subtopic in this chapter, which is social and economic aspects. Fermentation has many uses and is very important in terms of social and economic aspects. It covers a wide range of products such as from soy sauce to Interferon, antibiotic to biogas. Some products like food or vitamins are mature and will see a stable market but with decreasing prices. Other products, especially pharmaceuticals and biopolymers, are expected to gain economic importance in the future. So for the economic aspects, the economic value of food, feed and biotech pharmaceuticals is enormous, but fermentation contributes only a small part to the total cost. This is illustrated by antibiotics. The market value of the finished drug is certainly much higher than $20 billion per year. A toll manufacturer carrying out only the fermentation would get a fraction of this sum, probably less than 5%. Therefore, the value of fermentation itself is difficult to estimate. Next, the social aspects. There are a number of undisputed benefits connected with the production of food, feed, vitamins, and pharmaceuticals by fermentation. So these four is the benefits. The first one is the starting materials are from renewable resources. The byproducts are biodegradable and harmless. The third one, the production takes place under mild conditions, and the last one, the products are useful and low risk. Some of the important pharmaceuticals are produced by fermentation. They have changed the quality of life, at least for those who can access to them. Generally, experts expect that fermentation processes have economic advantages only for the production of expensive chemical, not for mass products. They expect more applications in the pharmaceutical field, where the active substances are valuable and difficult to produce by conventional chemical means.